Good morning, class. Today we're going to be defining Newton's second law. So the best way to really define Newton's second law is with an equation. So Newton's second law states that the sum of all the forces is equal to the mass times the acceleration, where both the force and acceleration are vectors. So both force and acceleration are vector quantities, and they're denoted with the little vector arrow above their letter symbols. This first letter here is actually the capital Greek letter sigma. And you may have seen it before in your math class. What it really means is the sum of. And so what we are doing is summing up all of the forces, the external forces that are acting on an object, to determine what is the net force. So sometimes you may see F sub net, but what I really like rather is the summation of the forces, and it is really the net force. They are synonymous. So sigma F is the same thing as F sub net. It really is the net external force that is acting on the object. So we can see that the sum of the forces, or sigma F, is actually the same thing as F net, or the net force. That's what we're saying. Also, this can be interpreted or rearranged a little bit such that the acceleration is equal to the net force divided by the mass. In this, we can see that there's a direct relationship between the acceleration and the net force. So the greater the net force on an object, the greater the acceleration would be. Whereas there's an inverse relationship between the mass and the acceleration. And we talked before that this mass is really representative or quantitative measuring of an object's inertia. And so the greater the inertia, the smaller the acceleration is going to be. So you can see this direct relationship between the net force and acceleration, and the inverse relationship between the mass or inertia of an object and its acceleration. These are all different ways to restate Newton's second law, and it's really the relationship of these three variables, which is often most showed here. As the net force is equal to the mass times the acceleration. Let's take a look at the units. Well, as it turns out, let's look at it from a mass and acceleration. We've already defined what the units are for mass, which are kilograms. And for acceleration, we should know that already to be meters per second squared. So with the mass being kilograms and the acceleration being meters per second squared, rather than every time we had to write the units for a force and saying a kilogram meter per second squared, we've given the name of the force to be represented and measured as a Newton. And that is in respect to Sir Isaac Newton, who this really is all about what he's observed. The fact that he came up with these three laws through his observations is pretty amazing. And so Sir Isaac Newton, which this course is really called Newtonian physics, where it's really the study of macro objects, their motion and how they move. So when you look at baseballs, footballs, planets, macro scale objects, it's what's referred to as Newtonian physics or the classic physics. And so the force is measured in newtons, and again, a newton is a kilogram meter per second squared. So let's take a look at the relationship here between the net force that's acting on an object, the mass of that object, and the acceleration that is caused by the net force.
Here we have a wooden box attached to a hanging mass set via a string that goes over a super pulley. Very little friction in the pulley. In its current state, there is no acceleration. The forces of friction are equal to the force of gravity on the hanging mass. But once we add additional mass to the hanging mass set, increasing the force of gravity, we have an acceleration. The force is greater and we have an imbalance of forces. If we add even more mass to the hanging mass set, we get an even greater acceleration. And here you can see the comparisons with the variation in the mass. Now, if we increase the mass in the wooden box itself, it actually increases the force of friction and is able to resist the pulling force from the force of gravity of the hanging mass set. However, if we add more mass to the hanging mass set, we can overcome the force of friction and create that imbalance of force and create a net force that causes acceleration on the box. Again, however, if we add more mass to the box, again, that additional mass at the box is going to increase the force of friction at the box, and we now have equilibrium and no acceleration.
So remember, every force has the ability to cause an acceleration, but it is really the net force that is acting on an object that will cause it to accelerate. And that's what will determine the acceleration of that mass. Objects can have multiple forces on them, but still not be accelerating. And that can be maintaining a constant velocity, both speed and direction, or not moving at all. Either one is really not accelerating or not changing my velocity with respect to time. So it's determining what the net force is and how that net force will cause an object to accelerate. Thank you, and I'll see you soon.